Welcome friends, I am Tanmoy. So today we will learn about Lindlar Catalyst. This Lindlar Catalyst is a very useful catalyst for the conversion of alkyne into cis-alkene. Means this is R1 and this is So, in this chapter, we will learn the conversion of alkyne into cis-alkene. Why this is important? Because generally, reduction of this alkene into cis-alkene is very difficult. What actually happens, if we see that if this is reduced in presence of hydrogen and simple palladium charcoal. Always keep it in mind to write hydrogen, because many times we write reducing agent but not the hydrogen gas. So don't make this mistake. And ultimately it results in complete reduction. That is alkene. But this is alkene. So for this purpose, what catalysts generally used are palladium, platinum, nickel, and they are so much active that in case of reduction with hydrogen gas that it end up in alkene. So it is important to have alkene. Second point, alkene is a saturated compound, so its reactivity is very less. You know that free radical, that type of very harsh condition is needed to function on this alkene, whereas it is very easier to convert this alkene into any other substance, for example using hydrogenation, hydroxyalkylation, demarcation, ozonolysis, etc. Many processes are there to convert these alkene into some other derivatives. Okay, because of this pi bond. And actually here two pi bonds are there and one pi bond is remaining here, so one is reduced. That is the main challenge of this process. So today we will learn about this process. First, we will see how this reagent, means Lindlar Catalyst, is prepared. Okay, this Lindlar Catalyst is prepared by the reduction of palladium 2, means PdCl2, in presence of excess HCl. Actually, this is not soluble. So that's why to make it soluble, excess HCl is needed. So after this, first sodium hydroxide is added, and actually the reduction, this palladium is palladium 0. This reduction is achieved in presence of sodium formate. Okay, and what happens this formate? This sodium formate converts into carbon dioxide and it produces hydride. Actually it's in situ, not separated hydride. This hydrogen is responsible for the reduction for preparation of this. And actually what happens during the reaction, this calcium carbonate is taken and over that this palladium reduction is happening, and this is actually a palladium nanoparticle. Okay, so it is not traditional simple palladium complex. This is palladium nanoparticle. And so first of all, we will discuss about the role of catalyst bed. Actually, this is called the catalyst bed, means calcium carbonate. This calcium carbonate could be used as a catalyst bed. Even barium carbonate could be used as catalyst bed, or barium sulfate could be used as catalyst bed. But there is a two category. One is carbonate category, one is sulfate category. Okay, so which is better? Actually, sulfate is better. Why? Because these carbonates are acid level, means acid sensitive, and ultimately, in presence of acid, they are capable to produce this carbon dioxide, which will ultimately destroy the catalyst bed. Instead of that, these sulfate do not have that problem. Even another question: is it possible to use any other than this traditionally used calcium carbonate, barium sulfate? Yes, possible. Alumina can do the job, but probably even better compared to this. But generally this information is not mentioned in commonly used books. So I suggest you keep it in mind if in your exam hall this is given. So don't be confused that this question is wrong. Okay. So this is the role of catalyst bed. Actually what catalyst bed is doing, it is acting as a support for the deposition of palladium in a very fine layer of palladium nanoparticle, which acting as a catalyst for reduction in presence of hydrogen gas. And actually hydrogen is added here. This is and this is. Okay. So this is the role. First of all, now we will discuss about the role of reagent. Reagent means actually palladium, it's a reducing agent I told. Hydrogen, palladium is catalyst and hydrogen is reducing agent, and generally palladium is added over 5%, very less. Next is lead tetraacetate. Lead tetraacetate, what it does, actually I told it's palladium 0 nanoparticle, it helps to activate those sites, those palladium sites which can provide selectivity, I repeat selectivity, for the reduction of this alkene. I explained previously this palladium is so much reactive that it achieves over reduction into alkane, but this provides active sites to give the selectivity for cis-alkene. Okay, this is the role of lead tetraacetate. Actually, this thing act as a catalyst poison. Poison means they inhibit the catalytic activity of this palladium center such that complete reduction should not happen. So this is their role. And second, what is quinoline? Quinoline is a molecule. It's like you can consider it's a benzene added pyridine. So it's electron deficient and it has a lone pair, and this lone pair is in sp2 hybridized. So always keep it in mind, this lone pair is not involved in the aromaticity. So this is quinoline. It coordinates to palladium center and which provides further selectivity for the reduction of alkyne into alkene, not the further reduction. I'll explain during the mechanism explanation. So, and this is 3,6-dithia 1,8 octanol. First let's write this. It is 1,8 octanol. So 2, 4, 6, 8, 1, see 1, 2, 3, 4, 5, 6, 7, 8. So 1,8 octanol means 1,8 octanol. Then 3,6-dithia. 3 sulfur, 3 sulfur and 6 sulfur. So this is the reason. In this way you should learn how to draw structure, because name should be given but you don't know the structure, and if you can't draw the structure it is very difficult to predict the reactivity, which then you will be confused to write the actual product, or you will be confused to get the answer properly. Now the question is about the solvent. Like other reaction, here solvent also plays an important role. What? This selectivity, solvent plays role. If we take very polar solvent like methanol, actually it's taken methanol and ethyl acetate mixture. Okay, so this is then the selectivity of cis and trans, cis versus trans reduces. What I mean, percentage of trans product increases. You can understand, it will be easy. But if non-polar solvent taken, for example, hexane with ethyl acetate, then this ratio improves. Improves means this improves means the amount of cis product increases. Okay, so actually what we wanted? Actually we wanted this cis product. That's why this is the choice of solvent. Okay, so this is the role of solvent. Now reactivity of alkyne. So you can see that actually alkyne is getting reduced. So it is dependent, it is expected that its activity also will play a role. It's true. What happens? Now this selectivity as well as mechanism I will explain. So what happens? Initially, this quinoline coordinates with this palladium 0 center. And one important information is that this palladium 0 is more electron deficient compared to traditional palladium 0 catalysts. Okay, so this is the uniqueness of this palladium calcium carbonate. This is called heterogeneous. This is a heterogeneous catalyst. What does it mean? Because it is not soluble in the reaction mixture. That's why it is called heterogeneous catalyst. So this is the uniqueness of this palladium on this calcium carbonate. That is a unique property of this Lindlar catalyst. That is electron deficient. That's why this quinoline coordinates as well as this acetylene coordinates. Okay. Now, question is, after the reaction, some alkene is produced. Why these alkene do not undergo further reduction? Okay. Before that, let me give you a brief description about hydrogen activation. What happens in case of palladium 0 when it reacts with hydrogen? I will draw in this, it will be better. That it gives electron to hydrogen and splits this hydrogen into hydrides. And this is actually oxidative addition of palladium. Okay, although the electronegativity difference between them is less, but this is oxidized and it is reduced. So in this way, so what happens? This palladium atom is also attached with hydrogen. Now I know it is very difficult sometimes for you to understand a palladium 0 nanoparticle is getting attached with hydrogen, is getting attached with alkene. It is too much complicated. I expect it. I also agree with you, it is complicated. But actually in case of nanoparticle, this phenomena is very difficult to understand and it's complicated. I agree. But I suggest you please accept the complication and enjoy the chemistry. Then you will have fun from this thing. And I will try to explain as maximum as I can. So this is what happens, it coordinates. Now I just asked sometime before that this is also, so it's a comparison that which will be added to palladium strongly. This alkyne has a 2 pi bond. Okay, and this has a 1 pi bond. So electron density over alkyne is more first, and second is that electron is at 2 pi bonds are there, and 2 pi bonds are 90 degree. Actually, what happens here? This, if we draw the HOMO and LUMO of the pi bond, but so 2p orbital forms a pi bond. This is the HOMO, positive, negative. This is HOMO, highest occupied molecular orbital. These are 2 carbons. Here also these are 2 carbons. And what does the LUMO looks like? LUMO looks like this. Plus, minus, this is anti-bonding interaction. Okay, so minus plus. Keep this strategy in mind and you can draw properly. What happens? This gives electron to the metal center. Okay, and this takes electron from the metal center. This LUMO, how? Form of interaction with the d orbital of metal. This is the palladium. So plus, minus, plus, minus. So in this way withdrawing and in this way donation. Generally it is said that this orbital is donated to dz square orbital and this is dxz and this is dxz yz. Okay. So 2 orbital accepts. So this is the expansion to bind, and here since alkyne has 2 pi bonds perpendicular to each other and more electron density compared to alkene, that's why this alkyne binds strongly. Second, if you check the donation of this quinoline, it is donating through lone pair, but it also accepts using the pi star, or actually the LUMO of this, and these we know it as like pyridine, and we know that pyridine is electron deficient, and this electron deficiency helps to withdraw more electron cloud from palladium, and if more electron cloud is withdrawn from the palladium center, then it becomes more electron deficient. That time it prefers the molecule which have electron in excess. So that is the alkyne. So that's why, in spite of having both alkene and alkyne in the reaction mixture, this catalyst prefers selectively to alkene. And after that, what happens? This hydrogen migrates here. Okay? Migratory insertion. So I'll draw it in this way. So this is palladium, one hydrogen is there, and if hydrogen migrates here, this center will be negative, because actually hydride migrating, not hydrogenic proton. So this will be negative, so this will bind to the palladium. So this is, and see, this is hydrogen, and palladium's hydrogenous position is like cis. You can remember such phenomena from the chemistry like beta hydride elimination, similar type. I am not saying exact, it's a similar type. So beta hydride elimination, in that case it is a saturated one, okay, but it is here, it is not unsaturated. So add this condition, you can see this hydrogen and palladium here, and second step, what happened? These hydrogen and this carbon eliminate. This is reductive elimination, okay, and what happens then? This hydrogen will migrate here and it will produce, this is the previous hydrogen, this one, and this hydrogen will come here, reductive elimination, and in this way, this is R1. So in this way, cis reduction is possible. Okay, okay. So I guess you have understood. So now we have explained the selectivity, this role. Oh, fine. So now the question is variety of substrate. For example, we have observed that this palladium is electron deficient. Okay, electron deficient. So it is expected that it will bind with electron rich. For example, if the alkyne contains some NH2 group, then what will happen? Actually, NH2 will bind. It binds, and that affects the selectivity. Selectivity means the proportion of cis isomer reduces and trans improves. So if in such cases, what is the solution? Solution is addition of amine previously such that it can't affect that much. For example, ethylene diamine or DMF. N-dimethyl formamide. Okay, this is methyl. So such type of solvent, that time if it is attached to electron rich, amine, if amine is there, then these nitrogen containing solvents are used. And even this reaction is so selective that in presence of double bond and triple bond, it selectively reduces the triple bond into cis-chloride. So this is the uniqueness of this reaction. And now the most important point which we will explain here, importance. Importance means where this process is applicable. Means, what do I mean applicable? For example, our target is to achieve cis-alkene, and it is not essential that we have to prepare cis-alkene from only acetylene. There should be other options. But if we do Barch reduction, then what happens? We take sodium and liquid ammonia. Okay, what it produces? Barch reduction produces trans R1. But another thing, for example, if we take dehydrohalogenation of alkanes, then what produces? Then also produces this alkene, but that is also trans. Why? Because trans alkene is more stable, cis-alkene is not. So, but if this process or reaction is giving selectively cis, So selectively cis, this means that this, since it's giving selectively cis, it means that this is a unique tool for the preparation of this cis-alkene selectively by metal hydride reduction, and more specifically controlled metal hydride reduction, because metal hydride reduction ultimately ends up the alkene. So this is the uniqueness of this process. So thank you everyone for listening my video. So if you have learned something or it is useful for you, then please like my videos, give us a thumbs up, and share this video among your friends such that many people could get benefited from my effort. And finally, subscribe my channel Chemistry, the Mystery of Molecules, and press the bell icon to get the notification of every single video I upload. So let's see you in my next video.